Hi again. In this second video here, we're going to look at a couple polynomial and rational inequality examples. So when an inequality is not linear, when it's got, like this one is a polynomial, so you see x squareds or anything bigger than just x. If it's rational, where there's a fraction with an x in the denominator, in that case we can't just use our regular algebra rules to solve these. Okay, we've got to take a different approach, and that approach is always to find the factors, to get the zeros, and to make a number line, right? So let's finish factoring this. We've got 4x squared, but I can do a difference of squares there, so we'll go with 4x squared times x plus 3 times x minus 3 greater than or equal to 0. And then all I'm going to do is make a number line here with my zeros. Since this is a polynomial, there's no undefined anywhere. I've just got these three zeros at -3, 0, and +3. Right? And so what's really happening here is, in a polynomial like this, the sign will only change when the inequality is equal to 0 at some point, right? So these are all places where it's equal to 0, okay? Notice we want to be greater than or equal to 0. So right now we can actually fill in each of these because each of those values will make the inequality true. Okay, and then we're going to test a value in each of the sections, or one of the sections. Let's start with a number smaller than -3, like -10 or -100. Let's think about that. That's going to give me positive, when I square x squared, times negative times negative. That's a positive value. Then if I tried something like -2, okay, we could go with, this is always going to be positive there when we're doing x squared. -2 makes this factor positive still, but the -2 minus 3 is negative, so this section's going to be negative. And then if I pick something like +2 for my third section, I'm still going to get positive. I'm going to get positive, but this one's still negative, right? And so I'm still negative there. Finally, in my last one, we are going to see that we get to positive times positive times positive, so back to positive there. Okay, so now I can see that my solution is anywhere where it's positive, because I want greater than or equal to 0. So that's those outsides there, but don't forget that this 0 is also a solution. So when we write our answer, when we write our interval notation solution, it's -infinity to -3 inclusive union 0 union 3 to infinity. Okay. We can also think about this from like a graphing polynomial perspective with the ideas of bouncing and crossing. Right? If I test one of the sections, let's say this one, I know it's positive, so I've got a polynomial that's going to look like that, and when it crosses the 0 at -3, it's odd multiplicity, so I know it's going to cross, so it's going to end up down below negative if I were graphing this polynomial. Then at 0, the multiplicity is even. X squared is even, so it's going to bounce and stay negative. And then at 3, multiplicity is back to odd, so it's going to cross again and end up positive. The values match, right? Positive there, bounces or crosses to go negative, bounces to stay negative, and then crosses to go positive. That's actually usually a little bit faster than having to test each section. Okay, now let's do a rational one. So in this example here, we've got 2x minus 7 over x minus 5 greater than or equal to 3. Just like before, if it's not linear, we cannot solve it the normal algebraic way. We've got to get it compared to 0 and put it in like a factored form kind of situation. So I'm going to get that 3 to the other side and get a common denominator. So we've got 2x minus 7 over x minus 5 minus 3, but then I'm going to get my common denominator, x minus 5 over x minus 5, and that's going to be greater than or equal to 0. When I combine this all, let's see what we get. We got over x minus 5. I'm going to have 2x minus 7 minus 3x plus 15 is greater than or equal to 0. And so that's what? Negative x plus 8 over x minus 5 is greater than or equal to 0. Okay, so the twist here is that not we have our zeros from the top, our x-intercepts, but we also have an undefined spot at x equals 5. So you have to take anywhere where the expression is undefined and include that in our number line when we do our number line test. So here, let's draw our number line. So in this case, I'm going to put the value that makes the numerator 0, which is 8. And I'm going to put anything that makes the denominator 0. That's automatically going to be an open circle because it's undefined there. Since we are greater than or equal to 0 at 8, I'm going to be filled in circle since I'm okay with equaling 0. And then same idea, we're just going to do a little number line test. We could also use the bouncing and crossing idea, but we do have to test one section first. I like the far left in this because I could plug in 0. And if I plug in 0 for x, I get positive 8, positive over negative. So I have a negative there. Let's go with the bouncing crossing idea, or diverge converge. My vertical asymptote here has a multiplicity of 1. It's going to diverge, so the sign is going to change. So that means we are going to be positive on this side. And then my x-intercept from the numerator has a multiplicity of 1 also, so it's odd. And so it's going to cross. So we're going to end up back negative over here. If you do the sign test, you'll end up the same spot. So positive, I am looking for greater than or equal to 0. That's positive, boom, right there. And so we end up with the solution 5 to 8, including 8. All right, there you go.